In the last class, we discussed the basics of the transport layer, and we said that essentially there are two protocols implemented, UDP and TCP. UDP just has a port number and it's going to perform just demultiplexing and sending the packets to the right application. And TCP is at the other extreme. It tries to do everything: reliable transfer, congestion control, ordering of packets, correctly sending packets in the correct order to the application, and so on. So today we will start looking at the details of TCP. So we said that there is a sequence number and an ACK number in a particular TCP segment. So what does this really mean? So suppose this is the sender, and this is maybe I shouldn't call it sender and receiver. Suppose this is A, whose A and B have a TCP connection between them, and this is over time. So A could be sending data this way, in which case acknowledgements would come back from B. Okay. But it's also possible that B sends data and A sends back acknowledgements for this particular data. Okay. So you can piggyback both of them. You can send data and an acknowledgement in one particular segment rather than sending two segments. Okay. So when you're sending out the data, you can also include an acknowledgement. So both of these fields are there in the packet, in the segment. The sequence number refers to the first byte in the segment, which byte it is in the entire flow. And the ACK number is saying, essentially it's telling you what I have received till now. Okay. And so you could have like a data plus ACK, where you're sending data in the segment corresponding to the sequence number given in it, and you also have an ACK number in it which corresponds to which particular data segment it just received. Okay, so roughly that's what's happening, and we look at the details a little bit later. So first thing is connection establishment. So how does a particular client, let's say, talk to a server? Right? So you might want to connect to the Google server, for example. And what exactly happens over there? So let's say that this is a passive participant let's say it's the server. So this particular server is listening. Maybe it has, it's a web server and it's listening on port 80. And I just say it's listening. And this is, let's say, a client which does an active open. So this particular client is going to connect. This could be you who's talking to the Google server. So what you do initially is you send out what is called a SYN packet. So this means that the SYN flag is set in the header. And let's say that the sequence number is X. Okay. So what does this particular server reply? So remember, it's a duplex connection, so data can go in both directions. It sends a SYN plus ACK. Okay, so the SYN is called, SYN stands for synchronization. They are sort of syncing up with each other. And this is the process followed when you set up the connection. So both SYN and ACK flags are set. And let's say that the sequence number is Y. And the ACK number is what? It's X plus 1. And finally, the third message in this three-way handshake, it's called. Okay, so I'm sending out a sync and I say that I want to start with sequence number X. So you might be wondering why don't we just start with 0 or 1, why do we start with anything X? We'll look at that in a moment. So this person, let's say the client, says that I want to start sending you data and I want to start with the sequence number X. Okay. And he says, he's replying with an acknowledgement, and he's also saying, I'm also willing to send you data and my starting sequence number is Y. Okay. So essentially here, SYN and FIN packets, let's say segments, don't have data. I mean, in the most basic case, they won't have data. But essentially they are counted, it's counted as if they have 1 byte in them. Okay, so in this example that I've shown, the SYN packet doesn't have any data. It's just the header, the TCP header going across, and it has sequence number X. So how are these two related to each other? So essentially, suppose this is, let's say, the whole file that you're sending. Now what we are saying is that the starting sequence number is, this is the file, and let's say that we write the sequence numbers here. So the sender is saying, I'm going to send you something starting with X. Okay, and this corresponds to the SYN. So it's considered as 1 byte, so it's not really part of the file. So the acknowledgement number that's going to come back is going to be X+1. So if you get an acknowledgement for a particular number, it means I got everything up to x. So I got everything from the start till 1 less than the ACK number. So in this particular case, it means I got everything up to x, and of course there was just 1 byte sent. Okay, so we are not, remember, we are not numbering starting from 0 or 1. This x can be anything chosen by the sender. So x is, usually it would be randomly selected. Okay. So I say x, and this person says, okay, I got byte x, which was your sin, and I am expecting the next byte to be x plus 1. Okay. So let's, okay, so this is let's say the file to go from client to server. Okay, essentially it's not necessarily a file. I mean, in real time, as somebody is typing information, for example, you can send it out on the TCP connection or the keystrokes. Okay, but this is a stream of data that is being sent from the client to the server. And so maybe I should write that. Let's just call it a data stream. And what about from the server to the client? The same thing, but very similar happens. So he is saying my sequence number is starting at y. Okay, so the client is going to send ACK number y plus 1. Okay. So here we just send ACK, and the ACK number is equal to y plus 1. So no data has been sent, but they have sort of synced up with each other, and they've told each other what are the starting sequence numbers. Okay. So this is the three-way handshake for connection establishment, and both of them have learnt each other's initial sequence numbers. Okay. So none of this is done with UDP. Okay. UDP, you just send out a packet to the destination IP address, and that's the end of it. You don't keep any records of what sequence number or anything is used, right? You don't care about that at all. Okay, so this is the three-way handshake essentially, and let's talk about why you choose these randomly. So why do you want a random x and a y? So suppose let's say that suppose we were transmitting a file. Or maybe not, okay, say we are transmitting files. Okay, so, and what I'm going to do here is I'm going to number the byte in the file. So this is, let's say, byte 0, and this is some byte n. Okay, suppose we started using sequence number starting from 0. Okay, so somebody, let's say that you sent out, you had a TCP connection to the server. Okay, you sent across the file, and you sent all the bytes out. Now what happens is you want to send another file. Okay, a second file. So I just say 0 to m. So you're starting out, and you start with sequence number 0. Okay. Now there is an issue over here that suppose you've started the second connection We don't know what happened to the first one. Maybe it's over. That's a possibility that the file successfully got transmitted. Or it could be that this was cut short, it was reset for some reason. So suppose you've transmitted a little bit up to here. This much was sent, and you're currently at this particular sequence number. It's possible that some particular segment over here was roaming around for some time in the network, maybe in a routing loop or something like that. And now it arrives at the server. Okay, so it's possible that this particular segment even reached the server. That may be possible. But there could be many copies of this segment floating around in the network. Maybe there was a retransmission or something like that, or a router replicated it, you never know. So this was floating around in the network for some time, right? This segment was sort of going around in the network, and then it reaches a little bit later at the server. So while you're transmitting this file, a segment from the old file might show up. And this could cause a problem because let's say that the port numbers are the same. Okay, so the server, let's say, is port 80, and you happen to use the same port number again for both. So these two connections are essentially indistinguishable. I mean, the IP addresses are the same, the port numbers are same, the transport protocol is both TCP in both cases, right? So this segment is going to come late, and the server might confuse it with a segment of the new file and may accept that particular segment. Okay, it may even send out an acknowledgement corresponding to this. Okay, so it may look like this. So this is the first file, and this is the second file. So this is a problem that you might face, and if you're starting from 0 all the time, if the sequence address is used by both of these are pretty much the same, all of them start from 0, go to n, whatever it is, right? There's a high chance that the sequence number of this segment may match something over here, right? So here, for example, even if this comes a bit late, I mean, even if you've only transmitted up to here and a segment comes for this portion, the person receiving it, in this case the server, might accept it. Okay, he might think that the segments in between were dropped or something, but he will accept this. So this is a problem if you have the sequence number space of both the connections overlapping. Some segment from the old connection which is delayed might confuse the receiver. He may think it's for the new connection. So that's the reason we choose sequence numbers, initial sequence numbers randomly. So we choose, let's say, this becomes x plus this, and this byte would be plus n plus x, right? And here, let's say that, okay, let's just call it x1 and x2. So here you choose another random number x2, right? So the hope is that these don't overlap, these two spaces, okay, so that you don't get confused, right? So this could happen, but there are other special cases too. I mean, nowadays we have very large files, so there is a problem, right? That maybe there is some overlap, but it's just that you hope that this, suppose you've already got this particular file, then you hope that this x2 is so far away from this n plus x1 that essentially that if any particular segment, let's say, comes from here, you cannot confuse it for something over here. Okay. So there are inbuilt rules. TCP won't just accept any particular segment. Maybe if it's a little bit ahead, it will accept it, but not too far ahead. Okay, but the idea is that you want these sequence number spaces to be somewhat far apart, so that what you expect, let's say over here, will be very different from what was sent out in the previous connection, at least towards the end of the connection. Okay. So these are chosen randomly, and what happens if the file actually is longer than the sequence number space allowed, right? I think there are 32 bits in the sequence number. So you might actually do a whole round and get back to sort of the original sequence number, right? So if we look at the sequence number space, so it's 0 and 2 to the power of 32. Okay. So this is just for a single file. I'm looking at that. So a single, if it's a small file, maybe it just occupies a particular range here. But if it's a very large file, it might occupy the entire space. So what you will do is you might go all the way around and come back to the original sequence. Okay, so that is possible. Okay, and you would just continue. You would sort of restart from this original sequence number. Okay, and the hope is that you don't have a segment from this region just floating around for so long that even when you come around here, that suddenly arrives, and then it causes a similar problem like we discussed about. Okay. But of course, maybe in the original internet they thought this is a very large number, and you'd never ever transfer files larger than that. Okay. But that's not true nowadays. Okay, so this is about starting the connection established state. Okay, so let's draw the state diagram for this connection establishment. And we'll see why we want to keep protocols simple. You know, we may get fancy ideas that I want to do this, I'll optimize this way, that way, and get performance improved. But then things get complicated very easily, and we'll see that even this sort of very simple protocol, right, with three-way handshake, will have a relatively complicated state diagram. And the more complicated, the harder to implement, harder to get things right. So this is the state transition diagram. So let's say we start with closed state. Okay, or let's say we are initially closed, and let's say we do a passive open. Okay. So I'm going to draw with dashed lines the states typically seen by the server. So we are in the listen state. Okay, so let's say the dashed line I'm going to write for the server, and let's say something like this would correspond to the client. So what happens to the server? Server is going to get, it's in the listen state, and it's going to get a SYN, and it's going to send out a SYN ACK, SYN plus ACK. Okay. So how are we going to write this state diagram? We are going to write it in the form of event and action. When you move from one state to the other, okay, either some event occurs and you take some action. Okay, so here of course the server itself is initiating a passive open, and it just moves to the listen state. It doesn't send out any packets or anything. Now what it does is what happens is it gets a SYN, that is the event, and the action is it sends out SYN plus ACK. So it goes to the SYN received state. And what happens now, once it's gone to the SYN received state after sending this out, okay, so we can just write this. So here we are in the listen state, and here we are in the SYN received state. And after we get back the acknowledgement, we are in the established state. So I'll use this solid line for the client. We can just see client and client, or let's say client. It's possible that it's the client and the server both reach those states. Okay, so obviously both start from closed and both end up with established. So let's see what the state diagram would be for the client. So we are initially closed, and what we are going to do is we are going to send out a sync. So we'll go to this SYN sent state. So we do an active open, and you send out a SYN packet. Okay. And now what happens? We are sort of looking at the client. So you have sent out this SYN. So remember, it comes here to the server, and this server sends out SYN plus ACK. So that is what we should expect. And we send out an ACK. The server sends out an ACK. Okay. So this is what the state diagram looks like for what we showed above. Okay, and TCP is implemented in as one module. It's not implemented as a client or a server or something. You don't have two separate TCP protocols. It's just one protocol. So this entire state diagram has to be implemented in the TCP protocol. So both the client and the server have this. The client machine might at some point decide to become a server. Okay. So you could do a passive open or an active open. Okay, and of course, in the example we showed, the server is going to go this way. I think I need to make this a dotted. And so let me just draw this. Now more interesting things can happen. So instead of having SYN/ACK, this is one way to open it, but you could have that somebody does a passive open, and somebody does an active open. So it could be that you are in listen mode, but then you yourself initiated a SYN, and they could cross over. Okay, so unlike the earlier case where you were only listening, so in this particular case you started out listening, but then you sort of actively started the connection. So you actively opened, and so you sent out a sync packet, and at the same time, let's say the other end also sent out a SYN. So that might happen, right? And we have to take that into account. So in this particular case, of course, you would send out an ACK for this SYN. You've already sent out your SYN, and here too you would send back an ACK. Okay, so this is another way of opening a connection besides just the three-way handshake. So what would that look like? Okay, and all of this has to be taken into account, right? Because you have to be prepared for anything that might happen. So in this particular case, the server is sending out, it gets a message to send, to actively start, and so it sends out a SYN. And what's going to happen, so it goes to SYN sent, and let's see, so here, so this is the server, and maybe let's use yet another color over here. So now where is the client? The client is already here, remember. So, okay, so the client has already sent out the SYN, and so it is over here. So the client is going to receive this SYN, and so it is going to send out let's say an ACK. Okay, so I got a SYN, and let's say I sent out an ACK, right? And then when I get an ACK, then finally it will be established. Okay, so we have to deal with these sorts of situations. Okay, and we have to be prepared for that, right? So it's possible that maybe even further possibilities are there which we would have to take into account, right? So if you look at any particular state diagram for TCP connection establishment, initially when you look at it, it will be very, very complicated, right? This thing looks something out of the sky, sort of, why are there so many states and so on. But really, many different things can happen. The default may be that you go this way, but maybe you will end up doing something else, right? Because you never know what the other side is going to do. So you have to take into account that there may be delays, maybe frames or segments are lost and so on, in which case you would have timeouts and so on. So all of that has to be built into the state diagram, right? And you can always close. So if you close a particular connection, you would go from any particular state to the closed state. So the actual state diagram, if you look up online, would be even more complicated than this, right? So designing and implementing protocols is non-trivial, and the more simple you make it, the better. Okay. So what about connection termination? So connection termination is when either side wants to call it quits. Maybe you've logged into a server or something like that and you're sending data. You could decide to stop the connection and quit. And how would this help the server when you actually quit? Well, because the server is actually maintaining some state information. Like this, for example, it knows which state it is in, it knows what are the next possible states and so on. It remembers your sequence numbers, what you have sent till now and so on, right? It keeps some buffer where it stores the segments that you sent. So a lot of state information is kept and a lot of data is kept for a TCP connection. So when you close, you're telling the other end that he can get rid of that state information. He doesn't have to maintain it, he doesn't have to maintain those buffers. So that's a good thing. When you want to quit, it's better that you actively quit and tell the other end that I am quitting. Okay? So there are various ways to do this, but essentially what we do is we use FIN packets. So you would set the FIN flag in your segments and you would that would signal to the other end that you want to end the connection. So we'll first talk about the half close. So this is closed by one end at a time. Okay, so one end is telling the other end that I don't want to send you any data. But the other end could say, okay, but I still want to send you data. So it doesn't close immediately, it will close a little bit later. Right? Or it's even possible to close simultaneously, which we'll look at next. So let's say this is a client and this is the server. Okay. And let's say that the client says that that a lot of data has gone in, let's say, both directions. Okay, so initially they opened over here with using sins and so on, and data was sent. Now the client says that I am done with sending you data, so I will send you a fin. And let's say that this has sequence number X, and let's say that the ACK number is Y. So what does the server do? So let's say that no data was sent over here in between, so he's just replying to this fin. So he's sending an acknowledgement, and he acknowledges that I have got your fin. Okay, so essentially what he's saying that ACK number is X plus 1, because we said sin and fin is considered as 1 byte. So I got your fin, and I haven't so essentially what I'm doing is I'm sending sequence number Y over here. Okay, and this is how it ends. Okay, so anyway, so this is one-way closing, and then you have data. And I beg your pardon, data goes in the other direction. You can still keep sending data here. So let's assume that this contains some data too. Okay, and you set sequence number equal to Y. And then let's say the other end decides to also finish the connection, and let's say it has sequence number Z and ACK number, let's say X plus 1. Okay, so your ACK number is going to get stuck after that, right? Like there's no more data coming over here, so you've received everything up to X, and you just ACK number, just say that I've got everything up to X, and I would expect X plus 1 if you were sending data. Okay? And from the other end, you finally close with this acknowledgement. So this is an ACK, you set the ACK flag, and your ACK number over here. So the sequence number, so what was your sequence number here? It's X. Okay, essentially you finished transmitting data, so you freeze it, and your ACK number is saying that I got your fin, which is considered 1 byte, so you ACK Z plus 1, right, saying that I got Z. So this is how it would end, and of course the state transition diagram is even more complicated than for the establishment case. right? Because you have to worry about cases of what if this fin packet is delayed or what if it is lost and so on, right? So there are various mechanisms for that, which is there you will find in any state diagram you look up for closing the connection. The last thing we wanted to discuss about the termination is the three-way handshake termination, where both close at the same time. So how does that work out? So this is the client, this is the server. So the client sends a fin. So the sequence number is X, ACK is Y. And the server also decides to call it quits. So it sends a fin plus ACK. So both flags are set in that particular segment. And the sequence number, let's say, is Y. Okay, so essentially what has happened is that I am sending 1 byte over here. Okay, so this is saying that I got everything up to Y minus 1. And I'm expecting Y. So this is of course the 1 byte I'm sending, it's Y. And the ACK number is going to be X plus 1. Okay, so it's saying that I got your this 1 byte of the fin. And finally, this is an ACK which says that I essentially got your fin. Okay. So I'm not sending any new information, so my sequence number stays the same. And my ACK number is going to be Y plus 1 because I'm saying that I got everything up to Y, including your fin. Okay. So this is how essentially we close the connection. Okay. So you can look up the full state diagram for connection establishment and closing, which looks actually quite complicated. Right? We have to deal with lots of issues like packets getting lost and so on, right? Or packets getting delayed. Right? So from the next class onwards, we look at other issues of TCP, things like congestion control and so on.